Hello Year 13 chemists, welcome to TP's Chemistry Cuts. In this clip we work through a question involving all the calculations on a titration curve that results when a weak base is neutralised with a strong acid.
Because we're going to start here, the only thing in solution at this point is CH3, CH3NH2. Okay? Let's work it through. At this point here, where we've got to the equivalence point, the only thing we'll have here is CH3NH3 plus. When we're halfway, what we're doing is we're going through from the weak base to its conjugate acid. So we've got a mixture of the two. So this is going to be our buffer zone. And here, what we've done is go beyond the equivalence point. So we're just adding in strong acid. So the pH is going to be mainly due to that, with a tiny, tiny amount due to the conjugate acid, but that's going to be insignificant compared to the amount of H3O plus that's been added by the strong acid. So I'll put HCl, but in fact what we're adding is H3O plus. Okay? So the calculations will first of all involve a weak base. Then we're going to look at a buffer calculation. Then we're going to involve a weak acid, allowing for dilution due to adding the base to the acid, acid to the base. And then at the end, another dilution effect where we're just looking at the concentration of a strong acid that's been diluted down by the acid plus the base plus the excess acid. Okay? So let's start with that first part here. And we must write out an equation for it because it's the only species in solution that is actually reacting with water to give a pH. And so we get this. And so, although I'll write out all the steps, you could go straight to the Kb is equal to the square root expression, but I'll put in the rest of the steps. This is the only reaction that's going on of any significance. So these two are of equal concentration. So we've got Kb is equal to the concentration of the conjugate acid times OH minus over the weak base. And so because these two are the same, that's OH minus squared over the concentration of CH3NH2. Okay, so what we want is OH minus as the subject of our equation because that's the thing that's going to give us the pH indirectly. So OH minus is equal to the square root of Kb times the concentration of CH3NH2. We haven't got Kb, but we can get it from Ka. So Kw equals Ka times Kb. Remember that. So we need to rearrange this to make Kb our subject. That's Kw over Ka. So we can now substitute that into our expression here. So now bring this up over here. I get the concentration of OH minus, which is what we want, is equal to Kb, the square root of Kb, which is Kw over Ka times the concentration of the base. And someone could calculate that for me, please? Which is, sorry, I'll put all the values in first, of course. 1 times 10 to the minus 14 divided by Ka, which is 2.29 times 10 to the minus 11 times the concentration of methylamine, 0.35.
0.0124.
Sorry, okay.
0.0124.
0.0124 mole per litre. Okay, so I'll just carry it along over here. You can calculate the pOH, which is minus the log of the concentration of OH, which is 0.0124.
1.91.
1.91. So the pH is equal to 14 minus 1.91, which is equal to 12.1. So the next step is midway to the equivalence point, so half equivalence if you like. So and when we're there, by definition, we've neutralised half of the weak acid, so the weak base, and turned it into the weak acid, or this conjugate acid, so we've got a 50-50 mixture. And so that's telling us the concentration of the weak base at that point is equal to the concentration of its conjugate acid. We've been given Ka for the acid, the conjugate acid, so I've written out the expression for the weak acid, and so we can write out, so the equation for it, the expression is equal to the weak acid, the weak base, the conjugate base for this particular equation, times H3O plus divided by CH3NH3 plus. Okay? We're saying that these two are equal, so these cancel out, so as you correctly said, yeah, this is equal to the concentration of H3O plus. So hopefully you can see that. It doesn't matter whether we're looking at Ka or Kb, they'll give you an expression, both will give you an expression in terms of these two concentrations, which is what we want. But we've been given Ka, we don't have to derive Ka like you do with Kb. So why not just use this expression to get this? So the pH is equal to the pKa, because pH is minus the log of that, so minus the log of that is the pKa. If somebody would tell me what minus the log of 2.29 times 10 to the minus 11 is?
10.6.
Okay. So that's our second point. So we have 12.1 here, 10.6 there. Okay.
Why did you put that equation?
This one here.
No,
Well,
the
we've been
one
given
above that.
that one there.
Yeah.
Yeah, because this is what we've been given.
Yeah.
Okay. So I'm writing out an equation for this.
Yeah.
Earlier on, we did this one because the only thing we've got in solution I've identified is that. So we need to write an equation for that, and that's for Kb. I'm just trying to keep things simple in the middle point, because we've been given Ka. Why don't we just use it directly? We could use Kb again, but then we've got to start using Ka over K, or Kw over Ka and things.
So we've put CH3 and HG plus on the left side because we want to use Ka.
Yes. Yes.
Because we want to
So what we're doing here is this is the equation that we can use. We know we've been given a Ka, and this is the equation, or the chemical equation that applies to the Ka.
Yeah.
So I've just written out the expression for Ka.
Yeah.
Now we know these two are equal, so that is equal to that.
Mm.
If I take minus the log of it, it's straightforward, because that's pKa and that's the pH, which is what I want at that point. I'm looking for the pH.
Yeah.
So whenever we're doing this, don't always go, what you've got to do is identify what you've got in solution. If you've got an acid in solution, use the Ka value. If you haven't, you've got to use Kb. Here, we've only got a base, so we've got to do things in terms of Kb. Yeah? Here we've got a mixture of the two, so we can go for the acid part. When we come to here, we will obviously go for the acid, because that's the only thing in solution that's reacting. Maybe I should have actually gone straight to the equivalence point and then gone back. I was just trying to keep things simple to begin with.
And so you use that with the weak acid tritrate with strong base.
Yes. Yes. So, as I say, the most important thing to do to begin with is identify which species are actually in solution, that are giving rise to the pH. So here you've only got the base, here you've only got the acid, in between you've got both. So here you've got to do an expression in terms of the weak base, here you've got to do it in terms of the weak acid, because it's the only thing there. Here you could do it neither. But it's easier to do it with the acid because you've been given Ka. You're always given Ka, or pKa, yeah? Because ultimately, you're doing a calculation of pH, so you need something that relates the concentration of whatever is reacting in the solution to the concentration of H3O plus or OH minus. And that's what the Ka or Kb does. Right, now, so we've got two. One thing before we move on is we can now mark in the buffer zone. So we know it's 10.6, so it's effective between 10.6, so it's 11.6 and 9.6, is anywhere between those two pHs is where there's going to be an effective buffer. Okay, so if this is 10.6, you'd mark plus 1 pH value above it, so which would be about here. And then plus 1 down below, which would be about there, and then you mark off here, there, and that's your buffer zone, yeah? Which has destroyed the pH calculation underneath. So if I label that now, yeah?
It's always plus 1.
Plus or minus 1, because that's the effective range of a buffer.
From 12.1.
From 10.6, so it go from 11.6 down to 9.6, yeah? So if I redo that, right then, so what I'll do now is we'll move on to the equivalence point calculation. Now this is the one that's a very long calculation. In fact, I think the first one's the harder calculation, and you're starting cold. By this time you're warmed up, as it were. What you've done is you've taken the weak base and you've converted it entirely into its conjugate acid. You've added just enough to do that. So the only species in solution now that's reacting is the conjugate acid. So if we know the concentration of this, we should be able to calculate the concentration of that. And we can do that because the amount of that, the weak base we start with, is now exactly the amount of the conjugate acid formed, because it's been entirely converted. The only thing that's changed is the volume. So what we've done in effect is to take that, dilute it by adding the water that we add with the base, and then convert it to that. So it's a diluted form of that we get here. To be able to calculate that, we need to work out what the volume at the equivalence point is. And I've just been nasty here and made the two concentrations different. Because if it was to say same concentrations, what would happen to the concentration at equivalence?
Half.
It would half, yes, because you just double the volume. But we aren't doubling the volume, so let's see what the volume is here. So, the reaction that we've done is taken CH3NH2 and we've added H3O plus to it to form CH3NH3 plus H2O. Straightforward neutralization reaction one way. Okay. So if we have n moles of this, it ends up as n moles of its conjugate acid. Now this is a 1-to-1 reaction. So to get from that to that, n moles of that to that, I need to add n moles of H3O plus. So n moles of this reacts with n moles of that to give n moles of that. Okay? Okay. So what we're saying in effect then is n of CH3NH2 is equal to N of HCl. It's a one-to-one neutralisation reaction. We know we've got N moles of that. So if I'm going to turn N moles of that into N moles of that, I need N moles of that. Yeah? So the two are equal. Yeah? So we know that, and this is given to you, but I don't know why. We know that C equals N over V. That will be on your sheet. Okay? So C times CH3NH2 times V of CH3NH2 is equal to C of HCl times V of HCl. Okay? So this needs to be the subject of our equation, and we'll get it right this time. Sorry, Trevor. Okay, so it's the volume of the base we started with, okay, times the concentration ratio. So it's V of this times C of this divided by the concentration of HCl. So in other words, the two volumes are related to each other by the ratio of concentrations, which makes common sense, really. Yeah? So that's our equation that, if you want to, you can memorise that and not work through it.
I like that.
Or you can work through it.
No.
Okay, so the volume of HCl is equal to the volume of amine, which is 20 over 1,000, times the ratio of the two concentration, which is 0.350 divided by 0.200. Somebody can work that out for me.
35 mils.
35. Yeah. Okay. And that makes sense because this is the more concentrated one you're starting with. You're adding a more dilute solution, so you expect to add a greater volume of it. So just use a bit of common sense to work it through. Okay? So now we've got the volume here. The next thing we need to do is look at what it is you've got that's causing the pH. Because we need an expression to calculate the pH. And it's the conjugate base. That's the only thing that's significantly causing the pH at equivalence. So very conveniently, we can write it underneath here. So we've got Ka is equal, well, why don't we write out the expression first so we don't get ourselves mixed up. NH3 plus H2O, because that's the reaction that we've got going on in solution at equivalence. Then we've got the weak base back again, plus H3O plus H2O. So we need Ka is equal to the concentration of CH3NH2 times H3O plus over the concentration of CH3NH3 plus. Okay. The only reaction going on, so those two are equal in concentration because it's nothing else to interfere with it. So the concentration of H3O plus squared over the weak acid. So rearranging this in terms of H3O plus, it's the square root of the concentration of CH3NH3 plus times Ka. Now we have Ka. We need to work out the concentration of the weak base. And this is purely a dilution effect now. We know the amount in solution because that has been converted to that. Okay? So we need the total volume, and that's why we calculated the volume of that. Now we could work through, like we did before, several steps. Alternatively, we could use the dilution effect, because we now understand this hasn't changed in amount, it's just been converted one to the other, but we've just increased the volume. So it's a dilution effect. So from our old equation, new concentration equals old con times V original over V total. The thing is, you must get the right things here. So what we're looking at, the new concentration, is that's been converted to that. So this is our concentration here, CH3 NH3 plus is the old concentration, which is what we started with as a base. Okay, so it's the concentration of the base at the beginning of the titration times its original volume, which is 20 over 1,000, divided by the total volume. So it's 20 over 1,000 is what we started with, but we've added 35 mils by neutralising them. So it's 35 over 1,000. Okay? Somebody calculate that for me?
So could you just keep it in mils? Since it came
Yes, so you can cancel the thousands out. You don't have to, I'm just being precise. And this value here is 0.35.
0.127.
0.127 mole per litre. So we can now substitute that into here. So the concentration of H3O plus
$1.707. 1.71
1.71,
times 10 to the minus 6.
and so the pH
5.77.
Okay, so that's the equivalence point. Now that we've got the pH at the equivalence point, which is 5.77, we can mark some more parts of the curve. Remember, the steep part here, for anything involving a strong acid, strong, be plus or minus 4 pH values. Because this is involving a weak base, then we need to go to 7.77, which is plus and then minus 2, okay, 5.77. And that should be the steep vertical, plus or minus 2 pH values. So if you have to sketch the curve, if you've got the pH of the equivalence point, you can then draw the vertical line, plus or minus 2 for it. And that means that all you've got left now is this point here, because then you're just drawing a curve due to addition of a strong base. Because we're at neutralisation, all you're doing is adding more and more, strong acid, more and more acid. Now, at this point, there is H3O plus in solution due to the conjugate acid. But this is an incredibly weak acid. So the concentration of H3O plus is going to be very low because it only partially dissociates. In fact, this is one of the weakest acids there is. So the concentration of H3O plus is going to be very, very low, and this is getting pretty close to 7. You think it's 10 to the minus 7 is 7, well this is almost 6, which means it's 10 to the minus 6. So that's 1/1,000,000th of a mole. So it's only going to take 1 or 2 drops of OH minus to actually put it back to neutral. Okay, or 1 drop probably. So if we start adding a strong acid to it, then that's immediately going to completely swamp out any effect due to this. So the pH is going to be pretty much entirely due to the added excess H3O plus from the strong acid. In other words, what we're doing is taking the strong acid, and so we say 20 mils, because we started with 20 mils to get to equivalence, but we'll say another 20 mils to go beyond equivalence, then, no, we had 35, didn't we? So if we had another 35 to go to twice beyond equivalence, then the pH is going to be due to the acid in that 35 mils, but we've got a lot of water in there initially due to the neutralization reaction. So the volume of acid we started with plus the volume of base that we needed to get to the neutralization point or the equivalence point, and then we've got this excess that we're adding. So what we're doing is literally just diluting the excess added. Okay? So why don't we do it over there? This is actually the simplest of calculations once you've got the general idea of what's happening in solution. So the last point will be pH when 35 ml of excess HCl added.
So which point is this on the cube?
So it'll be here.
Okay.
Okay? So that's just a line to tell you that we're assuming that the concentration of H3O plus in solution at this point here is due entirely to the excess strong acid added, because the amount or the concentration of H3O plus at equivalence is very, very small and insignificant when compared to the concentration that you're adding beyond equivalence. Okay, so yes, sir. So this is not moving around.
Nope.
Is it pointing over there?
No.
Nope.
Should we start again?
No, it's fine.
Stand over there so we can see it.
Okay. Sorry, Trevor. So that Trevor can see. So the pH when you add the excess, okay, this is what we're looking at this point here. So we've added excess acid, then we're saying that the concentration of H3O plus is entirely due to the excess added HCl, because the concentration of H3O plus at equivalence due to the conjugate acid is very, very small. It's insignificant when compared to the concentration added due to HCl. And so what we need to look at is what is the concentration due to this added excess HCl. And that is just a simple dilution effect. If we take that volume of HCl and say that we're adding in the water that was in solution at equivalence, then we get a new concentration. That's what we can use to calculate our pH. So we need our dilution effect calculation. So new concentration is equal to the old concentration times the original volume over the total volume. Okay, so our new concentration is the old concentration of acid now, because we're assuming it's due to the excess added acid. So that's 0.2 times the original volume. Well, we're adding 37 mils beyond, or 35 mils beyond. So we're going to leave it as mils because it's a ratio of volumes. Okay, so we've added 35, and we're adding that 35 to the 20 mils of acid or base in the flask plus the 35 mils to get to equivalence. Okay? So what we've got is the original acid, the base that we add to get to equivalence, plus the excess. So the original base, then the 35 mils of acid to get to equivalence, then the excess acid. So if somebody can calculate that for me.
When you say 35, you mean 0.0005?
Yeah. Well, in terms of mils, yes, but because it's mils divided by mils, divided by 1,000 to take it up to litres, you cancel anyway. So you don't need to. It's only when you're doing something divided by something in the same unit that it doesn't matter which multiplier you're using.
0.0778.
0.0778 mole per litre. So the pH is equal to minus the log of that, which is
1.11.
okay.